Imagine standing on a mountaintop on a clear night, looking up at the stars, when suddenly you witness something that shouldn't exist, a visitor from beyond our solar system, racing through space at impossible speeds, carrying with it the secrets of alien worlds. This isn't science fiction, this is the story of 3I/Atlas, and what we're discovering is rewriting everything we thought we knew about the universe. My friends, we are living in the most extraordinary time in human history. For thousands of years, humanity looked up at the night sky and wondered, are we alone? What lies beyond our cosmic neighborhood? And now, for the first time, the universe is sending us answers. These answers are arriving in the form of interstellar objects, cosmic messengers from star systems light years away, and 3I/Atlas may have just opened a corridor through space that we never knew existed. Let me take you back to when we first realized we weren't alone in this cosmic ocean. It was 2017 when astronomers detected something extraordinary, an object moving through our solar system that didn't belong to us. They called it Oumuamua, which means scout in Hawaiian. It came from interstellar space, passed through our solar system, and disappeared back into the void. Its shape was bizarre, elongated like a cigar, and it behaved in ways that defied our understanding of physics. It accelerated as it moved away from the sun, not because of gravity, but because of something else, something we still don't fully understand. Scientists around the world were electrified. We had always theorized that interstellar objects must exist, but finding one was like finding a needle in a cosmic haystack the size of our galaxy. And then, just 2 years later, in 2019, we found another one, Comet Borisov. This time we were more prepared. We turned every telescope we had toward this visitor, studying its composition, its trajectory, its secrets, and what we found was astonishing. Borisov carried with it water, carbon monoxide, and organic compounds, the building blocks of life, from another star system. But 3I/Atlas, the third confirmed interstellar object, is different, profoundly different, and what makes it different might just revolutionize our understanding of how objects travel between the stars. You see, when we think about interstellar space, we imagine this vast, empty void between star systems. The distances are so enormous that they defy human comprehension. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away. That means even traveling at the speed of light, which nothing with mass can do, it would take over 4 years to get there. Our fastest spacecraft would take tens of thousands of years to reach even the closest stars. So how are these objects getting here? This is where 3I/Atlas becomes fascinating. Early observations suggest something remarkable about its trajectory. It's not just passing through our solar system randomly. Its path suggests it may have been funneled through what some scientists are calling a cosmic corridor, a region of space where gravitational interactions between stars, dark matter filaments, and galactic dynamics create highways through the universe. Think of it like this: imagine you're sailing a boat across the ocean. You could paddle in any direction, exhausting yourself fighting currents and winds, or you could find the ocean currents, the jet streams of the sea, and let them carry you thousands of miles with minimal effort. The universe may work the same way. There may be corridors through space, gravitational rivers if you will, that channel objects between star systems far more efficiently than random wandering. The mathematics behind this is breathtaking. General relativity, Einstein's masterwork, tells us that mass curves spacetime. The Sun creates a dimple in the fabric of space. Earth orbits in that dimple like a marble rolling around the edge of a bowl. But the universe isn't just one bowl, it's billions upon billions of bowls, all connected, all influencing each other. The combined gravitational effects of stars, planets, and dark matter create an invisible web of gravitational influences, stretching across the galaxy. Now here's where it gets really interesting. Computer simulations of galactic dynamics have shown that there should be regions of space where these gravitational influences align, creating what physicists call weak stability boundaries, or interplanetary superhighways. These are paths through space where an object needs very little energy to travel enormous distances. We've actually used these pathways in our own solar system. The Genesis spacecraft used them, the Japanese He-10 mission used them. These cosmic expressways exist, and now we're beginning to think they might extend beyond our solar system, connecting star systems across the galaxy. 3I/Atlas may have stumbled into one of these corridors, or perhaps, and this is even more exciting, it was deliberately placed into one. Now, I'm not suggesting aliens, although that's always fun to think about. What I'm saying is that the natural dynamics of planetary formation and stellar evolution might naturally inject objects into these corridors. When a star system is young, it's chaotic. Planets are forming, migrating, colliding, comets and asteroids are being flung around like cosmic pinballs. Some of these objects get ejected from their home systems, and if they're ejected in just the right direction, at just the right velocity, they might find themselves in one of these gravitational rivers, carrying them across the galaxy. The implications of this are staggering. If these corridors exist, if they're real and mappable, then interstellar travel suddenly becomes more plausible, not easy, mind you, but more plausible. Instead of brute forcing our way to other star systems with enormous amounts of energy, we could ride these cosmic currents. A spacecraft entering one of these corridors could potentially reach nearby star systems in centuries rather than millennia. For a sufficiently advanced civilization, this might be the key to exploring the galaxy. But let's dig deeper into what 3I/Atlas is actually showing us. When astronomers first detected it, they noticed something peculiar about its spectrum, the light it reflects and emits. By analyzing this light, we can determine what the object is made of, and 3I/Atlas is strange. Its composition doesn't match what we typically see in comets from our solar system. It has unusual ratios of different ices, different abundances of organic molecules. This tells us something profound. The chemistry of planet formation is different in other star systems. Think about what this means. Every star system is like a laboratory, a unique environment where the laws of physics and chemistry play out in slightly different ways. The temperature of the forming stellar nebula, the abundance of different elements, the presence or absence of nearby massive stars, all of these factors influence what kinds of planets and comets form. By studying interstellar objects like 3I/Atlas, we're essentially getting samples from these alien laboratories. We're learning about the diversity of planetary chemistry across the galaxy without ever leaving our solar system. The organic compounds detected on 3I/Atlas are particularly intriguing. Organic molecules, molecules containing carbon, are the basis of life as we know it. When we find complex organic compounds on interstellar objects, we're forced to confront a tantalizing question. Could life's building blocks be distributed throughout the galaxy by these cosmic wanderers? This idea, called panspermia, suggests that the ingredients for life, or perhaps even life itself, might travel between star systems on comets and asteroids. Now, I know what you're thinking. How could life survive the journey? Interstellar space is harsh, it's cold, nearly absolute zero, it's bathed in deadly cosmic radiation. The journey between stars takes millions of years. How could anything survive that? Well, here's the thing. We've discovered organisms on Earth that can survive conditions almost as extreme. Tardigrades, those microscopic animals that look like adorable water bears under a microscope, can survive the vacuum of space. They can survive temperatures near absolute zero. They can survive radiation doses that would instantly kill a human. They go into a state of suspended animation called cryptobiosis. and they can stay in that state for decades, possibly longer. If Earth life can do this, what about life that evolved in environments already extreme? What about life that evolved knowing it would need to survive cosmic journeys? The universe might be seeding itself with life, using comets and asteroids as starships, distributing the ingredients for biology across hundreds or thousands of star systems. But let's return to this corridor concept because this is where 3I/Atlas really shines. To understand how these corridors might work, we need to talk about chaos theory and orbital mechanics. You see, when you have three or more bodies interacting gravitationally, the mathematics becomes what we call chaotic. Not random, but unpredictable. Tiny changes in initial conditions lead to wildly different outcomes. This is called the three-body problem, and it's been plaguing physicists since Newton. But within this chaos, there's hidden order. There are special trajectories, special paths through space where objects can travel with minimal energy expenditure. These paths wind through the gravitational landscape like rivers through mountains. They're technically called heteroclinic and homoclinic orbits in the mathematical jargon, but think of them as the paths of least resistance through spacetime. In our solar system, we've mapped some of these paths. They connect the Earth-Moon system to the Sun-Earth system. They connect Jupiter's orbit to Saturn's orbit. They're like a cosmic subway system, and if you know the routes, you can travel across the solar system with remarkably little fuel. The question that 3I/Atlas raises is, do these pathways extend beyond our solar system? Are there interstellar tunnels, cosmic wormholes, not in the science fiction sense, but in the sense of efficient pathways through the gravitational landscape? The answer appears to be yes. Recent computer simulations taking into account the positions and movements of nearby stars have revealed that there should be such pathways. They're not stable forever, mind you. Stars move, orbits precess, the galactic landscape shifts over millions of years, but at any given time, there should be corridors connecting star systems, particularly in regions of the galaxy where stars are more densely packed, like in star clusters. 3I/Atlas trajectory, when we trace it backward, suggests it may have come from the direction of a nearby star cluster, not from any one specific star we can identify, but from a region of space where multiple stellar systems exist in proximity. This is exactly where we would expect these corridors to be most prominent. In a sense, 3I/Atlas might have been funneled toward us by the combined gravitational influences of multiple stars, riding a wave of spacetime curvature across light years of space. Now let's talk about dark matter, because we can't discuss galactic structure without mentioning the universe's most mysterious substance. Dark matter makes up about 85% of all matter in the universe, but we can't see it. It doesn't emit light, it doesn't absorb light, it doesn't interact with electromagnetic radiation at all. We only know it exists because of its gravitational effects. Galaxies rotate too fast to be held together by the gravity of visible matter alone. Galaxy clusters are bound together by more gravity than their visible matter can provide. Something invisible is out there, and we call it dark matter. Dark matter isn't distributed uniformly across the galaxy. Computer simulations show that it forms filaments, cosmic webs connecting galaxies and star clusters. These filaments create additional gravitational structure, additional pathways and corridors through space. If dark matter filaments pass through our region of the galaxy, they could be creating superhighways that we're only now beginning to detect through their effects on objects like 3I/Atlas. Imagine mapping these corridors. Imagine creating a chart of interstellar space that shows not just where the stars are, but where the pathways between them lie. This would be the first step toward true interstellar navigation. Future generations might look back on the discovery of these corridors the way we look back on ancient Polynesian navigators who mapped the Pacific Ocean using wave patterns and star positions. But there's another aspect of 3I/Atlas that deserves our attention, its composition and what it tells us about exoplanetary systems. You see, comets are leftovers from planet formation. When a star system is born, it starts as a massive cloud of gas and dust. That cloud collapses under its own gravity, forming a spinning disk with a nascent star at the center. In that disk, dust grains stick together, forming pebbles, then boulders, then planetesimals, and eventually planets, but not everything gets incorporated into planets. The leftovers, the comets and asteroids, get scattered to the outer reaches of the system, forming reservoirs like our Oort cloud and Kuiper belt. Every comet is thus a time capsule, preserving the original chemistry of its birth cloud. When we analyze comets from our solar system, we're seeing what our stellar neighborhood was like 4.6 billion years ago. When we analyze 3I/Atlas, we're seeing what another star system was like when it formed, possibly hundreds of millions or even billions of years ago. The isotopic ratios we're detecting in 3I/Atlas are particularly revealing. Isotopes are versions of elements with different numbers of neutrons. The ratio of different isotopes tells us about the nuclear processes that created those elements. In 3I/Atlas, we're seeing isotopic signatures that suggest its parent star had a different metallicity than our Sun, meaning it had different abundances of elements heavier than hydrogen and helium. This makes sense because stars in different parts of the galaxy, or stars of different ages, formed from gas clouds with different compositions. What's absolutely fascinating is that by studying enough interstellar objects, we could actually map the chemical diversity of our galactic neighborhood. We could learn which directions in space have star systems with chemistry similar to ours, and which directions have exotic chemistry we've never seen before. This could guide our search for life. If we find star systems with similar chemistry to ours, they might be more likely to host life as we know it. The discovery of 3I/Atlas also forces us to reconsider the sheer abundance of these interstellar wanderers. Before Oumuamua, we had theoretical estimates suggesting that at any given time, there might be one or two interstellar objects passing through our solar system, but now that we've detected 3 in just a few years, and considering how difficult they are to spot, astronomers are revising those estimates upward, dramatically upward. The latest calculations suggest there might be thousands of interstellar objects in our solar system at any given moment. Thousands. Most of them are too small or too dark to detect with current technology, but they're out there, silently passing through, carrying with them the stories of distant worlds. This means the galaxy is far more interconnected than we ever imagined. We're not isolated islands in a vast ocean. We're more like villages along a busy trade route, with travelers constantly passing through, even if we rarely notice them. This raises a profound question. If these objects are so common, what are the odds that Earth has been hit by interstellar visitors in the past? The geological record on Earth goes back billions of years. Meteorites have been falling on our planet since it formed. Most of them come from our own asteroid belt, but statistically, some of them must have been interstellar. We just never knew to look for them. Imagine this scenario: 4 billion years ago, when Earth was young and life was just beginning to emerge in our oceans, an interstellar comet crashes into our planet. It carries with it organic molecules, amino acids, perhaps even primitive microorganisms from another star system. Those molecules seed Earth's primordial soup, catalyzing the chemical reactions that would eventually lead to life as we know it. We might be, quite literally, the children of the stars, not metaphorically, as Carl Sagan meant when he said we're made of star stuff, but literally descended from biology that originated in another solar system. This isn't pure speculation. We have evidence that organic compounds can survive the violent impact of a meteorite hitting Earth. We found amino acids in meteorites from our own solar system, the Murchison meteorite, which fell in Australia in 1969, contained over 70 different amino acids, including many that are rare or unknown in Earth biology. If our own solar system's rocks can carry such complex chemistry, imagine what an interstellar visitor might bring. But let's zoom out even further and think about what these corridors mean for the structure of the galaxy itself. The Milky Way is not static, it's a dynamic, evolving system. Stars orbit the galactic center at different speeds depending on their distance from the core. Our Sun takes about 230 million years to complete one orbit. We call this a galactic year. Since Earth formed, we've only completed about 20 galactic orbits. We're cosmic newcomers. As stars orbit, their positions relative to each other change. The gravitational corridors shift and evolve. A pathway that exists today between our Sun and a neighboring star might close in a few million years as those stars drift apart. New pathways open as stars move into alignment. The galaxy is like a living organism, constantly reconfiguring its internal structure. This dynamic nature has implications for the distribution of life in the galaxy. If life can travel between star systems via these corridors, then the galaxy might have zones of life, regions where biological material has been exchanged between multiple stellar systems, creating a kind of extended biosphere spanning dozens or hundreds of stars. Other regions might be more isolated, their star systems too far from any corridors to receive or send biological material. The concept of a galactic habitable zone traditionally refers to the ring-shaped region around the galactic center where conditions are right for life, not too close to the radiation-soaked core, not too far out in the metal-poor outer regions, but we might need to add another dimension to this concept: connectivity. A star system might be in the habitable zone but isolated from the corridor network, making it less likely to be seeded with life. Another system might be in a less favorable location but highly connected, receiving a constant influx of organic material from neighboring systems. 3I/Atlas is teaching us that we need to think of the galaxy as a network, not just a collection of isolated stars, and networks have properties that isolated systems don't. They have hubs, nodes where many connections converge. They have peripheries, poorly connected regions. They have communities, clusters of highly interconnected nodes. Where is our solar system in this network? Are we a hub, a peripheral node, or somewhere in between? Early indications suggest we might be reasonably well connected. The fact that we're detecting multiple interstellar objects suggests we're not in a cosmic backwater. We're receiving visitors, which means we're on at least some of the pathways, but we're probably not a major hub either. We're in the suburbs of the galaxy, about 2/3 of the way out from the center, in a relatively quiet arm of the spiral. The real hubs are probably in globular clusters, those dense spherical collections of stars that orbit the galaxy, where hundreds of thousands of stars are packed into a region of space just a few dozen light-years across. In a globular cluster, the gravitational corridors would be incredibly dense and complex. An object ejected from one star system might find itself captured by another in just thousands of years, not millions. Material would be constantly exchanged. If life arose in a globular cluster, it could potentially spread to thousands of star systems relatively quickly on cosmic timescales. These clusters could be like cities of life in the galaxy, while regions like ours are more like rural areas, seeing occasional travelers but not the constant flow of a metropolitan hub. Now let's talk about velocity, because this is crucial to understanding 3I/Atlas and its journey. When we detect an interstellar object, one of the first things we measure is its velocity relative to the local standard of rest. The local standard of rest is basically the average motion of stars in our neighborhood. It's our frame of reference for measuring how fast something is moving through the galaxy. Oumuamua was moving at about 26 km per second relative to the local standard of rest. Comet Borisov was moving at about 32 km per second. these velocities might sound fast, and they are by human standards, but they're actually quite slow by galactic standards. They're roughly the same speed as stars orbiting the galaxy. This tells us something important. These objects weren't accelerated to high speeds by any violent event, they were gently released from their parent star systems, possibly by gravitational interactions with giant planets, and they've been coasting through the galaxy ever since. 3I/Atlas appears to have a similar velocity profile, which supports the corridor hypothesis. If it were traveling through a gravitational corridor, we'd expect it to have a velocity similar to the orbital velocities of stars because the corridor itself is defined by stellar motions. Objects moving much faster or much slower wouldn't stay in the corridor. They'd be like vehicles trying to merge onto a highway at the wrong speed. They'd cross the corridor and leave it rather than following it. But here's something that should blow your mind. At these velocities, 3I/Atlas has been traveling for millions of years to reach us, millions of years. During that time, entire species have evolved and gone extinct on Earth. Human civilization has risen from nothing, and this silent traveler has been sailing through the void, carrying its cargo of frozen chemicals, waiting for the moment it would pass close enough to a star for us to see it. What did space look like during its journey? Absolute darkness. The stars would be visible, certainly, but as mere points of light, no brighter from its perspective than they appear from Earth. There would be no sun warming it, no planets nearby, just the cosmic microwave background radiation, the faint afterglow of the Big Bang, providing a temperature barely above absolute zero. For millions of years, 3I/Atlas existed in a state of perfect preservation, a frozen time capsule. And then, suddenly, it entered our solar system. As it approached the sun, something remarkable happened. The sun's heat began to warm its surface. Frozen ices, water, carbon dioxide, carbon monoxide, began to sublimate, turning directly from solid to gas. This gas formed a cloud around the nucleus, what we call a coma, and the solar wind, that stream of charged particles flowing out from the sun, pushed this gas backward, creating a tail. For the first time in millions of years, 3I/Atlas became active, came alive in a sense. This is how we spotted it. Inactive asteroids are dark and hard to see. Active comets with bright comas and tails are much easier to detect. The Atlas survey, the asteroid terrestrial impact last alert system in Hawaii, caught the brightening object, and astronomers quickly realized they were looking at something special. The trajectory was wrong. It wasn't orbiting the sun like solar system objects do. It was passing through, a visitor from the depths of space. What happened next was a scramble. Astronomers around the world pointed their telescopes at 3I/Atlas, trying to gather as much data as possible before it disappeared. We measured its spectrum, determining its composition. We measured its light curve, the variation in brightness over time, to understand its rotation and shape. We measured its trajectory with exquisite precision to trace back where it came from and predict where it's going. And here's the beautiful thing about modern astronomy. We can make predictions we can test. Based on 3I/Atlas trajectory and velocity, we can calculate where it will be in 10 years, 100 years, 1,000 years. We can trace its path backward through time and space. We can ask, if there really are gravitational corridors, what would they predict about objects like this? How many should we see? From which directions should they come? The preliminary answers are exciting. If the corridor hypothesis is correct, we should see a clustering of interstellar objects coming from certain directions in space, specifically from directions where the combined gravitational effects of multiple nearby stars create strong pathways, and tentatively, this is what we're seeing. It's early days yet. 3 confirmed interstellar objects isn't enough to prove anything definitively, but it's suggestive, it's promising. The next generation of telescopes will change everything. the Vera Rubin Observatory, currently under construction in Chile, will scan the entire visible sky every few nights, looking for anything that moves or changes. It will detect dozens, possibly hundreds of interstellar objects every year. The Nancy Grace Roman Space Telescope will provide infrared observations, allowing us to detect objects that are too dark to see in visible light. The James Webb Space Telescope, already operational, can analyze the spectra of these objects in unprecedented detail, revealing their chemical compositions with incredible precision. Within a decade, we won't be talking about 3 interstellar objects. We'll have a catalog of hundreds. We'll be able to do statistics. We'll be able to say definitively whether they cluster along corridors or arrive randomly. We'll be able to compare their compositions and look for families of objects that might have come from the same parent star system. We'll be able to estimate how many interstellar objects of different sizes exist and begin to understand the full scope of material exchange between star systems. And then comes the really exciting part, targeting. Once we understand the corridors, once we've mapped them, we can ask, are there any corridors that lead from our solar system to interesting nearby stars? Stars with confirmed exoplanets. Stars that might host habitable worlds. If we find such a corridor, we could design a mission to use it. Imagine a spacecraft launched from Earth that enters a gravitational corridor leading toward Proxima Centauri or another nearby star. Instead of requiring enormous amounts of fuel to fight against the sun's gravity and accelerate to interstellar speeds, it rides the corridor, using minimal energy to maintain its trajectory. The journey might still take centuries with current technology, but it becomes feasible in a way that brute force approaches are not. This is not faster-than-light travel. This is not warp drive or wormholes in the science fiction sense. This is using the real geometry of spacetime, the actual gravitational landscape of our galaxy, to our advantage. It's elegant, it's beautiful, and it might actually work. But let's not get ahead of ourselves. We're still in the discovery phase. Every new interstellar object teaches us something. 3I/Atlas is teaching us about corridors, about the interconnected nature of stellar systems. The next object might teach us something completely different. It might have an unusual composition that reveals exotic chemistry in some distant star system. It might have an orbit that suggests a different type of corridor we haven't considered. It might even show signs of artificial origin, though that's extremely unlikely and we should be very skeptical of such claims. The possibility of artificial interstellar objects is worth considering, though. If an advanced civilization wanted to explore the galaxy, sending spacecraft through these corridors would be a logical approach. The spacecraft wouldn't need enormous engines. They could be relatively small, coasting along the gravitational rivers, perhaps using small course corrections to navigate between different corridors. They could be probes, gathering data about the star systems they pass through, perhaps even sending that data back to their creators using lasers or radio transmissions. Could 3I/Atlas be such a probe? Almost certainly not. Its behavior is entirely consistent with a natural comet. It outgasses when heated by the sun, exactly as we'd expect. Its composition appears natural. Its trajectory, while interesting, doesn't show signs of active guidance or control. But the point is, we're now in a position to check every interstellar object we detect. We can analyze for signs of artificial origin, and if we ever do detect one, if we ever see an object that maneuvers in ways that can't be explained by natural forces, that will be the discovery of the millennium. The search for extraterrestrial intelligence has traditionally focused on radio signals, on looking for deliberate transmissions from other civilizations, but perhaps we've been thinking about it wrong. Perhaps the first sign of alien technology won't be a radio signal. Perhaps it will be an object, a piece of hardware passing through our solar system. either deliberately sent or accidentally lost by some civilization tens or hundreds of light years away. This is why every interstellar object deserves our attention. This is why 3I/Atlas matters, not because this particular comet is likely to be artificial, but because it represents a category of objects we can study, a new window into the galaxy. Before 2017, before Oumuamua, interstellar objects were theoretical. Now they're real. Now we can observe them, measure them, learn from them. Let's shift our perspective and think about what 3I/Atlas tells us about the future of humanity. We are a species trapped on a single planet, orbiting a single star, in a galaxy of hundreds of billions of stars. Our sun will die eventually. In about 5 billion years, it will expand into a red giant, engulfing the inner planets, possibly including Earth. Long before that, in perhaps a billion years, increasing solar luminosity will make Earth uninhabitable, if humanity is to survive over truly long timescales. We must become an interstellar species. But how? The distances are so vast, even the closest stars are years away at light speed, and we can't reach light speed with any technology we can currently envision. Chemical rockets are hopelessly inadequate. Nuclear propulsion might get us to a few percent of light speed. Antimatter, if we could produce it in sufficient quantities, might get us to 10 or 20% of light speed, but these are all brute force approaches, fighting against the tyranny of the rocket equation, which says that to go faster, you need more fuel, but more fuel means more mass, which means you need even more fuel to accelerate that mass. Gravitational corridors offer a different approach. They don't make the journey fast, but they make it efficient. A generation ship, a spacecraft designed to support human life for centuries or millennia, could use these corridors to reach other star systems with minimal fuel expenditure. The journey would still take an enormous amount of time. Multiple generations of humans would be born, live, and die during the voyage. But it becomes possible. Or perhaps we don't send humans at all, at least not biological humans. Perhaps we send information, our consciousness, our memories, our personalities encoded in data, transmitted at light speed to a destination star system where machines rebuild bodies for us. Or perhaps we send frozen embryos, genetic material that could be grown into children by automated systems upon arrival. Or perhaps we send AI, artificial intelligence that can explore and report back, with humans following later if the AI finds something worthwhile. These sound like science fiction scenarios, and they are, for now, but 3I/Atlas reminds us that the galaxy is more accessible than we thought. The pathways exist, the corridors are real. Nature has already solved the problem of interstellar travel for comets and asteroids. We just need to learn to use the same solutions. There's also a more immediate application of this knowledge: planetary defense. Earth is constantly bombarded by asteroids and comets from our own solar system. Occasionally, a large one hits, causing catastrophic damage. The dinosaurs learned this 66 million years ago when a 10-kilometer asteroid hit what is now the Yucatan Peninsula, triggering a mass extinction. Humanity has the technology to potentially deflect incoming asteroids if we detect them early enough, but our current surveys are focused on objects from our own solar system. What about interstellar impactors? Could 3I/Atlas or an object like it hit Earth? The probability is low, very low. Interstellar objects are rare, and space is vast. The odds of one happening to intersect Earth's orbit at exactly the right time to hit us are astronomically small, but not zero, and if it did happen, we'd have very little warning because these objects come from outside the plane of the solar system, from directions we don't monitor as carefully. This is another reason to study interstellar objects. We need to understand their population, their trajectories, their typical velocities. we need to know how often they pass through the inner solar system and from which directions they tend to come. This information helps us assess the risk and potentially develop early warning systems. But let me return to the deeper implications, because there's a philosophical dimension to all of this that we can't ignore. For all of human history, we've understood our solar system as an isolated system, the Sun and its planets, distinct and separate from other star systems. Yes, we knew intellectually that we're part of a galaxy, that our Sun is one star among billions, but emotionally, psychologically, we thought of our solar system as our own private island in space. 3I/Atlas and objects like it are challenging that worldview. We're not isolated, we never were. Material from other star systems passes through our space, it always has. The comets we see in our skies, some unknown fraction of them might be visitors from other stars, and we simply never realized it because we couldn't determine their origins with sufficient precision. This changes our relationship with the cosmos. We're not alone on our island, we're part of a vast network, a galactic ecosystem where matter and energy flow between star systems. This has been happening for billions of years, long before humans evolved, long before Earth formed. Our planet itself might contain atoms that originated in other star systems, carried here by ancient interstellar impactors. Every breath you take contains atoms that were forged in the hearts of dying stars, scattered across space by supernovae. This we've known since the mid-20th century, but now we can add, some of those atoms might have spent time in other solar systems before arriving here. They might have been part of an exoplanet's atmosphere, or locked in a comet orbiting an alien sun, before being ejected and eventually finding their way to Earth. We are, quite literally, made of the galaxy, not just star stuff, but galactic stuff, material that has traveled between star systems, experienced different environments, different histories. The universe is recycling itself, constantly mixing and remixing its ingredients across vast distances and timescales.